Hello everyone. In this video, we are going to count the number of ways to arrange letters on the vertices of a cube. And the letters are going to be repeated, so you have to count it carefully. And also, two configurations obtained through rotation of the cube are considered identical. So we should not be overcounting. And the two letters A are supposed to be placed on opposite vertices of a face of the cube. They should not be anywhere random. The configuration has two A's, two B's, two C's, and two D's. And in any configuration or arrangement, you should have the two A's on diagonally opposite vertices of a face of the cube. This problem is inspired from SuMON level 2, fortnight 29. And let's get started. So, here is the question we are trying to solve. You are given with the letters AA, BB, CC, and DD. Let us construct a cube now. This is the front face, and let's consider this as the back face. And you have the lateral sides. Let's color it with blue. Now, if we are just wondered about the number of possible arrangements without any constraints, it would just be 8 factorial, permuting all the 8 letters onto the 8 vertices of the cube, because each vertex will have 8 possibility for the first, and for the first letter you will have 8 possible vertices, for the second letter 7 possible vertices, and so on. But you have two identical letters. You cannot allow the permutation between these two letters. For example, A being filled up here and here cannot be permuted between themselves, because that will yield the same permutation, and therefore we divide it by 2 factorial. Similar argument for B. So this entire thing is divided by 2 factorial, and the whole thing is divided by 2 factorial. So you will get 2 factorial division 4 times. So the answer would be 8 factorial by 2 factorial into 2 factorial into 2 factorial into 2 factorial. So this accounts for the repetitions of the letters, as we do not allow the permutation between the repeated letters. So this is not the final answer, because if you rotate the cube, one permutation gives the entirely other permutation. Say you rotate along the axis joining the centers of the front and the back faces of the cube. So this will give you one more permutation. Say you rotate by 90 degree, 180, 270 and 360. So 4 rotations will give you 4 permutations, or maybe some 2 of these permutations are just the same. So having these, we cannot conclude the final answer to be 8 factorial upon 2 factorial into 2 factorial into 2 factorial into 2 factorial. But we can case wise count by fixing the positions of A. So in the question, we have one additional constraint that the two A's are required to be at diagonally opposite corners of the face of the cube. So this means, considering the bottom face of this cube, let's fix the point, the letters A. Notice that a permutation or a rotation of the cube with axis passing through the centers of top and bottom faces will rotate the A here onto the A here, and same this one goes to this one. So they will get exchanged. So now we have to consider, or at least we will use that rotation to make sure that we are not overcounting. Because if you do not consider that rotation, then probably you are overcounting that rotation with the actual original one. For example, if you have B here and B here, C here, D here and D here, when you perform that rotation about A, about the center line joining centers of top and bottom faces, you will get the two A's exchanged, which will put the same configuration at the end. But the positions of B, C, D will change. That will give you a completely different permutation of the letters on the vertices of the cube. So now we have to consider this rotation before counting the entire number of permutations. So let's call this rotation as R. So it is the rotation about line joining centers of top and bottom faces. Alright, so now we have fixed the positions of A. This means you can only perform this rotation. All other rotations shall change the position of the two A's. So these are absolute and they are fixed. A's are fixed. Now let's consider the possibilities for B. There are three places of B that stand alone. What are they? Suppose you fix B and B here and B here. Or you fix B, B here. Or you fix B and B here. These two are diagonally opposite points of a particular face of the cube. When you fix B's over that position, upon this rotation R, you will get also the positions of B fixed. This means you are completely getting the same permutation of the letters. So that means if A and B are rotated, you will get B to this and B to this, which does not change the configuration of the letters. So let's count that a little later. For now, you have there are remaining 6 vertices, and you choose 2 vertices to place those B. But now, since you can perform this rotation R alone, you have to divide this by 2. Because when you perform this rotation, you're going to get a different configuration. So you have to club that different configuration with the original configuration. So that's why you divide by 2. But before dividing by 2, are we sure that all configurations yield different configuration upon this rotation R? No. If acted upon this permutation, some of the configuration that we saw will not yield a different configuration, and hence they should not be divided by 2. So we first subtract them, and that is 3 in number. That happens when the letters B are in diagonally opposite positions of a face. So we subtract 3 and divide by 2, and then we add 3. Alright. So this gives us 6 choose 2 is 15 minus 3 upon 2 plus 3, and that would be 6 plus 3 ways. 6 plus 3 ways to place the B's. So first we are placing the 2 B's. Later we will place the 2 C's. Later we will place the 2 C's. So as I mentioned, let's come to the other 3 ways a little later. Focusing on the 6 ways to place the B's, you are going to get a different configuration when you perform the rotation R, which means you cannot perform the rotation R now. The configuration is going to be unique as the positions of A and B are fixed. And after this, you will have 4 choose 2 ways to place the C's, as there are 4 remaining vertices on the cube. So the frontal face like this, the back face like this, and the lateral sides like this. You have placed the A's over here. Suppose say you have placed the B's over here. Then you have 4 places, 1, 2, 3, 4 places to choose from for the position of C. Since you cannot perform, you have to completely count it, and that gives us 6 ways. Now after these 6 ways, the remaining 2 positions are automatically occupied by the 2 Ds. Coming to the other 3 ways for placing the Bs, you cannot get rid of the rotation R, because by performing it you will not change the positions of the 2 Bs, right? So you have to consider the rotation R. Supposing the A's are here and the B's are in the bottom face but in the diagonally opposite corners of it. So you have the entire top face, and note that my argument can be easily carried forward for each of these 3 ways. So concentrating on the top surface of the cube or the top face of the cube, you can place the 2 C's in 4 choose 2 ways. Again, it is 4 choose 2. But out of these, since you can perform that rotation R, you will get some 2 configurations the same by performing it. So you have to subtract the configurations that yield the same after performing R. So you can do that in 2 ways, because placing C and C in the other 2 diagonally opposite corners of a face will yield the same configuration of C's, and hence there will be no change. So the remaining should be paired up, clubbed together by 2. So since each configuration is going to give exactly one more configuration, as we have removed all the similar yielding configurations, you have to divide by 2, but finally you have to add that to those 2 ways in which C can be filled so that it yields the same configuration, and this gives us 6 minus 2 by 2, that's 2 plus 2, which equal 4 ways. So for the 3 ways to place the 2 B's, you have 4 ways to place the 2 C's. So this is interesting, right? So total count can be done now. So we analyze this case by case, from placing the A's to placing the B's and to C's. The D's will have only one way, because the remaining 2 places are just for the D's. There are no other permutations among them. The total ways would just be 6 ways for placing the B's. So remember, I am fixing the A's in the bottom left and the bottom right corner of the bottom face, in the top right corner of the bottom face. So totally there are 6 ways for the 2 B's. In that you have 6 other ways to place the 2 C's. And for the 3 ways, the distinguished 3 ways to place the 2 B's, you have 4 ways to place the 2 C's. This gives us 36 plus 12, and that's 48. So this is the final answer. So we solved a lot of interesting real life problems like these in our SuMON math, and we also provide a solution manual to the students at the end of each fortnight. So we will meet you in the next problem solving video. Until then, happy learning. Bye.